So, in this chapter, we've been talking about concentration, and I want to talk about one of the reasons that concentration is important. And to do that, we need to focus on our biological cells. So, we have biological cells, and they have a cell membrane, and the cell membrane looks like this. It's two layers, it's called a bilayer. And the cell membrane mediates the interaction of the cell with its environment and is responsible for the passage of materials into and out of the cell. Now, it does this in a couple different ways. One of the ways that it does this is diffusion, and that's just the net movement of solute or solvent molecules from an area of high concentration to low concentration. Right? Because of the structure of the cell membrane, only really small molecules are able to diffuse freely or pass through it freely. And so I have two images here for you, and one is a high concentration of solution. This would be like the interior of a cell, and this is a low concentration of solution, and we've got a cell membrane. And water likes to go from a low concentration solution to a high concentration solution. Basically, water is trying to dilute everything. And so you would expect the water flow to go this way. Other things that diffuse across a cell membrane are things like gases, oxygen, nitrogen, those types of things. Sometimes this is called passive diffusion or simple diffusion. Now, there are other ways that things can get across cell membranes. You can have facilitated transport, where you have a channel that's formed by a protein and things go across it that way. Or you can have active transport where it also requires energy, right, like ATP. But that's not really what we're going to focus on. Right now, we're more interested in this passive flow of small molecules across the membrane. Now, because of the way the membrane works, it is called a selectively permeable membrane. So permeable means it'll let things across. Selectively means it doesn't let everything across. Sometimes it's called a semi-permeable membrane. So when we talk about this, it's important to also talk about osmosis. So osmosis is the diffusion of a solvent which in biological cases is water, through a semi-permeable membrane in response to a concentration gradient. Okay, and so what we know is that water flows from low solute concentration to high solute concentration. So water is always trying to dilute things, okay? Now, there is a pressure that builds up here, and that pressure is called osmotic pressure. And with this, the pressure, this is the pressure exerted to stop the flow of water, right? So this is the pressure, right, that we need to stop the flow of water, to keep all that water from rushing in. And we have one more term, and then we're gonna solve a problem. And that other term is osmolarity, right? And this is just the molarity of particles or ions in solution. So it's a lot of times the molarity times I. So it equals the molarity times I, where I is just the number of particles. It's sometimes called the Van Hoff factor. So if you hear it called that, that's what they're talking about. So for example, NaCl forms Na plus and Cl minus in solution. So that means its Van Hoff factor is 2. Na2SO4 forms 2 sodium ions and SO4 2 minus, and so that means its Van Hoff factor is 3. It's just the number of ions. So osmotic pressure is shown with pi. Now this pi does not equal 3.14, right? It just means, this pi means osmotic pressure. And so we can say, look, osmotic pressure, pi, equals the Van Hoff factor, or the number of particles, times the molarity, times our friendly gas law constants back, R, times T, okay? So let's look at an example where we calculate the osmotic pressure. So calculate the osmotic pressure of a 5 times 10 to the negative second molar solution of NaCl at 298 Kelvin. So when we look at this, we're calculating osmotic pressure. And so we know that formula is pi equals I times mRT. And we've got a value here, and that's molarity. And so that's one of our context clues. We have temperature, which is 298 Kelvin. And then we have NaCl, which we know breaks apart into Na plus and Cl minus. So there's 2 ions there. So I equals 2. We also know the gas law constant. It'll be given to you on this test. Right? So when we talk about this, right, pi equals 2 times the molarity, which is 5.0 times 10 to the negative second moles per liter, times R, which is 0.08206 liters times ATM over moles times Kelvin, times the temperature, which is 298 Kelvin. And so when we look at this, Kelvin cancels here, moles cancel here, liters cancel here, and we're left with ATM, which is a unit of pressure, and remember pi here is osmotic pressure. So we do this math, and with rounding to 2 significant figures, we get 2.4 ATM. And that's the osmotic pressure, right, to keep water from flowing into a cell. Okay. Now, that's not always the case, so let's talk about red blood cells for a second. So when we talk about red blood cells, right, we can put red blood cells in different solutions. And one of the things that we can do is we can put red blood cells in a solution where outside the cell it's got a lower concentration of solutes than solution inside the cell. So let's put some words to that definition. This is just a solution outside the cell having a lower concentration of solutes than solution inside the cell. Okay, so what this means is that you have a cell here, okay, and it's very dilute outside the cell, right? And it's really concentrated inside the cell. And so what happens is that, that's weird. What happens is that water rushes in, right? And makes the cell very large. So now the cell is very large to the point that it can burst. And this is called hemolysis. If you like root words, lysis, right, is the word for like burst, right? So you see that if you're really into biology. And so one of the ways I remember this is we have hemolysis. This gets to be a very large cell. It's hypotonic. There's an O there, and the cell gets really, really large. If that works for you, that's great. If not, just ignore that last 15 seconds. Now, you can have a hypertonic solution. This is where you have a solution outside the cell with a higher concentration of solutes than inside the cell. So you have your friendly cell here again, right? It's very concentrated outside the cell, right? And so the water rushes out of the cell and it gets all crinkly, right? It shrivels up like if you put a pickle in salt water, right? It's going to shrivel, or a cucumber in salt water, it's going to shrivel. For example, if you put a cucumber in salt brine or salt water, it shrivels, right? That's what you see kind of happening here. If you want a fun experiment to do at home, my suggestion is to get some gummy bears and put gummy bears in just a solution of water and measure them over the several days. And what you're going to see is the gummy bear gets larger and larger. And then put a gummy bear in a solution of salt water. And what you're going to see is that this gummy bear gets smaller and smaller. Gummy bears are made of, they have some cells in them. They have a lot of protein. And so that's always a really fun experiment if you're having a hard time conceptualizing this, that is super fun. So these things shrivel up, and that's called crenation, right? And so, as you can imagine, neither of these environments are very good for a cell. And so a lot of times cells are in isotonic solutions. And this is where a solution outside the cell has the same concentration as inside the cell. All right. So I love pictures, and so I wanted to show you a picture of this. When we look at this, this is a normal red blood cell. It's got a little dent in it. This is an isotonic solution where the water is going back and forth at the same rate. Here's a hypotonic solution where the water is really flowing in and making this a lot bigger, and you can see that these cells have lost their little indent. They're getting really poofy. And then here's a hypertonic solution where the water is leaving and the cells are crinkling up, right? So these are red blood cells, and that's crenation. As always, if you have any questions, please feel free to stop by my office.